So chapter 9 is gas power cycles. Okay, so power cycles means these cycles produce power. So it's just like heat engine, heat engine or like a turbine, but this is a little bit complicated than a single turbine. So but very similar to the heat engines we have learned in chapter 6, I think. Okay. And the gas here means the working fluid for these cycles. Okay, so gas like air or air fuel mixture, things like this. So this is a gas power cycles. And actually in chapter 10, chapter 10 is steam power cycles. So instead of gas, in chapter 10, the working fluid is steam. Okay, but we won't go to chapter 10. Okay. All right. So first, let's look at this power cycles. What is power cycle? Okay. The devices or systems used to produce a net power output are called engines. So just like heat engines we have learned in chapter 6. And the thermodynamic cycles that they operate on are so-called power cycles. Okay. So power cycles are cycles that these engines operate on. Okay, and these engines are used to produce a net power output. Okay, so these are power cycles. On the other hand, although we won't go to refrigeration cycles as well, just like steam power cycles, but refrigeration cycles are for the devices or systems used to produce a refrigeration effect. And refrigeration effect is actually to transfer heat from a low temperature reservoir to a high temperature reservoir. Not necessary to be reservoirs, but maybe I should say transfer heat from low temperature medium to a high temperature medium. Okay, so this is refrigeration cycles. So just like refrigerators, air conditioner, and heat pumps. So we have learned this in chapter 6 as well. Okay. So thermodynamic cycles can be classified by the phase of the working fluid. For example, for this chapter, we are focusing on gas power cycles. So that means the working fluid remains in the gas phase throughout the entire cycle. And another phase is like vapor phase. So we have vapor cycles. That means the working fluid exists in the vapor phase during one part of the cycle and in the liquid phase during another part. Okay, so it's like a liquid phase, liquid and vapor like phase change process. Okay, but here we give it a name called vapor cycles. Okay, but we will focus on gas cycles in this chapter. So we can also classify the thermodynamic cycle by operating style of the working fluid, closed cycles and open cycles. So for closed cycles, that means the working fluid is returned to the initial state at the end of the cycle and it's recirculated. So the working fluid is not renewed every thermodynamic cycle. That is the closed cycles. But for open cycles, the working fluid is renewed at the end of each cycle instead of being circulated. So just like the automobile engines, like car engines. So we know basically car engines, for every thermodynamic cycle, the air fuel mixture is like repelled out of the engine and new air fuel mixture coming into your engine to be burned. Okay. So that kind of cycle is called open cycles. Okay. heat engines. Okay. So heat engines can be classified by how the heat is supplied to the working fluid. So we have so-called internal combustion engine, okay, or IC engine. It's initial IC. So IC engines are internal combustion engines. So that means the combustion happens inside the system. Okay. So heat is done by burning the fuel within the system boundaries. So that is so the internal combustion, and later we will talk about external combustion. That means where the combustion takes place. Okay, internal combustion means the combustion takes place inside or internally within the system boundaries. Okay, then external combustion means the combustion takes place externally or outside of the system. Okay, so IC engine, it operates on a mechanical cycle. The working fluid does not undergo a complete thermodynamic cycle. That is the very unique characteristic of an internal combustion engine. Okay. Working on an open cycle is the characteristic of all internal combustion engines. So that means the working fluid is renewed every thermodynamic cycle. That makes sense, right? Because internal combustion, that means the combustion happens internally inside the system. So after combustion, there's a exhaust gas, and this exhaust gas has to be repelled, has to be renewed, or otherwise there will be no combustible gas inside the system to be burned. And okay, so burning the fuel means to provide the heat or to provide the energy. Okay. External combustion, such as steam power plants. So this belongs to chapter 10. So we won't go to external combustion. Okay. So heat is supplied to the working fluid from an external source, such as furnace, geothermal well, and nuclear reactor, even the sun. Okay. So this is how the energy is supplied to the system. Okay. So if the energy is supplied to the system within the system, that means the combustion happens inside the system. That is internal combustion engines. Okay. If the engine is supplied by the external source, then that kind of engines are external combustion engines. Okay. Ideal cycle. Okay, so to make an analytical study of a cycle feasible, we have to keep the complexities at a manageable level. So that means we should assume some kind of assumptions. We need to make some assumptions to simplify the reality. Okay, but at the same time, we still need to keep some levels of the complexity so that the assumed ideal case will be not too far away from the reality. Okay, so we need to make some idealizations or assumptions. Okay, so just like these two cases. Okay, so we know potato. Well, a potato is made of a lot of integrated components or nutrition, things like this. So a real potato is not very homogeneous. Homogeneous means the properties doesn't change over location, but apparently for potato, maybe there's a I don't know, defect. Well, defect is not so precise, but maybe a cavity here, small cavity here, but there's a large cavity here, and maybe there's some kind of worm here, things like this. So the material inside a real potato is not homogeneous. Okay, so this is the actual one. So, but to analyze the characteristics of this potato, maybe we could assume a bulk of water to replace the analysis of a real potato, because we know at least water is a pure substance. So the material properties are homogeneous. Okay, and we can control the shape as well. A tank of water could be in a bucket, and this bucket may be very rectangular or something. Okay. So in this case, it's ideal. So we can control the mass, we can control the shape, we can control the volume, etc. Okay. So because water is very well known, all the material properties are well known, things like this. But to keep the complexity, maybe some properties, maybe the shape, maybe the mass should be the same as a real potato. Well, depending on what kind of analysis you want to perform. Okay. All right. So ideal cycles, when the actual cycle is stripped of all internal irreversibilities and complexities, we end up with a cycle that resembles the actual cycle closely, but is made up totally of internally reversible processes. So like this, on a PV diagram, the actual cycle is the pink dashed line, okay? But after the idealization, after making some assumptions on these actual cycles, so you can see the black solid line, at least here, this process is constant volume process, right? Compare with this pink one. So this pink one is not a constant volume, but it's not too far away from a constant volume process. So we just make an assumption that we assume this process is constant volume, and that would be enough. That would be accurate enough. Okay. Similar stuff happens to this side. Okay. So you can see the pink dashed line. This is not a real constant volume process. Okay, but very close, So when we are analyzing the cycle, we could just assume it's very close to a constant volume process. Okay. All right. So ideal cycles are internally reversible, just internally reversible. We don't care what happens outside of the system. Okay, we just care what happens inside the system, and we assume there's no internal irreversibilities. So that means inside the system it's reversible, and in this case it's just internally reversible. Okay. Then, unlike the Carnot cycle, we know Carnot cycle is the best one, right? It's made up of 4 reversible processes, right? And all the processes are reversible. And Carnot cycle has 2 compression processes, 2 expansion processes, and 2 isothermal processes, and 2 adiabatic processes, right? So Carnot cycle is still the best. Okay, it's still the best. And Carnot cycles are totally reversible. So totally reversible means that process is internally reversible. It's also externally reversible. So together it's totally reversible. Okay. but that is just for Carnot cycle. And you need to know that a Carnot cycle is unable to be achieved in reality, right? Because reversible process doesn't exist. Okay. Then look at this. The efficiency of an ideal cycle in general is less than that of a totally reversible cycle operating between the same temperature limits. Okay, because totally reversible is internally reversible, it's also externally reversible. But ideal cycle, an ideal cycle is only internally reversible. So the thermal efficiency of an internally reversible cycle is still less than the efficiency of a totally reversible cycle if these two cycles are operating between the same two temperature limits. Okay. But however, the thermal efficiency of an internally reversible cycle is still considerably higher than that of an actual cycle because of the idealizations, because the assumptions we made on this internally reversible cycle. Okay, so don't forget, ideal cycle in this case in chapter 9 refers to just internally reversible. Okay. All right. Then, okay, so to make a cycle ideal, we need to make some assumptions. We need to make some idealizations or simplifications. Okay, so what are these simplifications? Okay, the idealizations and simplifications commonly implied in the analysis of power cycle can be summarized. First one, the cycle does not involve any friction, such as working fluid does not experience any pressure drop as it flows in pipes or devices such as heat exchangers. So this is something about fluid mechanics. So we know, you can walk forward, it's because of the friction, right? Similar to the fluid can flow forward, it's also because of the friction. So friction, friction is actually caused by the viscous effect. Okay, so like if you have a flow coming through this pipe, and the flow can be seen as layer by layer structures. Okay, so or if you want, you can consider the fluid layer as a fish. Okay, so let's say if you have a fish, this is a fish. Okay, this is a fish. Moving forward, this is another fish. Moving forward, this is another fish. Just like this, okay. And these fish, they are very compact. So when they are moving, then this bottom fish is dragged by the wall. This is the pipe wall. Okay, so just imagine if this fish is laid down on the wall, it's very difficult for it to move or to swim forward, right? Because there are very strong friction between this fish and the wall. Okay, and on top of this fish, this second fish, this guy, this second fish, the second layer is a second fish, want to move forward as well. But this fish will be like, will have the friction between the bottom one, the bottom fish, right? So when the second fish, this fish wants to move or swim forward, then there will be a drag or there will be a friction between it and the bottom one. Okay, so that is the layer by layer concept. Okay, so that's why when a flow is flowing through a pipe, then there will be a pressure drop, and this pressure drop means this pressure drop comes from the viscous effect. Okay, so and we know pressure is actually the energy, but energy per unit volume. So when pressure drops, that means energy drops. Okay, so this is the idea. But for ideal case, we just assume there's no friction. There's no friction. So there's no pressure drop when the working fluid flows over a pipe. Okay, that's the first one. The second one, all expansion and compression processes take place in a quasi-equilibrium manner. So quasi-equilibrium, we have mentioned this a lot. So quasi-equilibrium means it's equilibrium, but and the equilibrium, this kind of equilibrium is a result that the process takes place so slowly so that there's a time for every molecules inside the system like self-adjust to be uniform everywhere. So the material properties inside the system are uniform, are homogeneous. Okay, that is what quasi-equilibrium means, right? So quasi-equilibrium is it's an equilibrium, but it's an assumption because when the system volume is expanding or being compressed, then you know the material properties around this area will be probably different from the material properties at this area. But quasi-equilibrium here means the process happens so slowly so that the material can adjust by itself so that to make the material property at this area is the same as this area, is the same as everywhere. Okay, so basically quasi-equilibrium is just equilibrium. Okay, but in microscopic point of view, this is what happens. Okay. Third one, the pipes connecting the various components of a system are well insulated. Okay, so there's no heat transfer inside or outside. Okay, I mean to the system or from the system because the system is well insulated. Sorry, no, the pipe connecting various components, like for example, like a heat engine, right? Remember, we have a heat engine. So a heat engine is made by like 4 components like this, right? In chapter 6. Okay. So these arrows, this is the pipelines. Okay. So these pipelines are assumed to be well insulated. Okay, there's no heat transfer to these pipes, or there's no heat transfer out of this pipe. Okay, so for the pipe, we assume there's no friction and it's adiabatic. Okay, so 2 assumptions just for the pipes. Okay, and these pipes are used to connect various components. So like this, connect a turbine and connect the boiler or the condenser, things like this. Okay. Then we also neglect the changes in kinetic and potential energies of the working fluid, which like we have been using this assumption a lot. Okay. All right. Then PV diagram and TS diagram. So we know PV diagram, the area underneath PV diagram represents the boundary work, right? and the area enclosed by the process curves on a PV diagram represents the network, right? So this is the network. This is the network. Okay. And for TS diagram, so similar to a PV diagram. So the area underneath a process curve on a TS diagram represents the heat transfer, right? Then the area enclosed by the process curve on a TS diagram represents the net heat. But in this case, the net heat is the same as the network, right? If the system is well insulated, if the system is well insulated, from the energy balance point of view, then you can see this is not necessary to be well insulated. Well, there must be a heat transfer, right? So it's not insulated. So I mean, from energy balance, because this is a cycle, so delta E system is 0. So the for these two, it could be by heat and work for a closed system. Then Q in, work in equals Q out plus work out, right? So if you combine the heat and you combine the work, you can see the net work out is the same as the net work in. Okay, so that's why here is net work is also the net work. Okay. Okay. So let me see. Look at this. On PV and TS diagrams, the area enclosed by the process curves of a cycle represents the network produced during the cycle, which is the same as the net heat transfer for that cycle. Okay. An ideal power cycle does not involve any internal irreversibilities, and so the only effect that can change the entropy of the working fluid during a process is heat transfer. Okay, all right. So on a TS diagram, from chapter 7, we know that if you add you add some heat to a system, then the delta S is larger than 0, right? This system receives some heat, so the entropy of this system increases. So the heat addition process proceeds in the direction of increasing entropy. So that is the reason, right? If you input some heat to a system, you would make the entropy of this system increases. So that's why the heat addition process proceeds in the direction of increasing entropy. Okay. So the area under the heat addition process on a TS diagram is a measure of the total heat supplied during the cycle, which is the Q in. So this is actually the Q in, heat addition. Okay. Similarly, for heat rejection process. So heat rejection process proceeds in the direction of decreasing entropy. Okay. So if you have a system like this and there's a heat loss, and you can see or you know the entropy of this system decreases because the heat is lost. Okay. So the area under the heat rejection process is a measure of the total heat rejected, which is Q out. Okay. Then an isentropic process. So isentropic means reversible and adiabatic, right? So an isentropic process proceeds in a constant entropy. Well, of course, isentropic means constant entropy. TS diagram, the area under the process curve on a TS diagram represents the heat transfer for that process. Okay, so this is pretty much the statement for the statements in this slide, right? Then the area enclosed by a cyclic curve is the net heat transfer, which is also the net work produced during the cycle, which is the statement here, okay? So the net heat is also the net work. So we can write this. Net work is net heat. They're the same. This is from the energy balance, right? Okay. The ratio of the area enclosed by a cyclic curve to the area under the heat addition process curve represents the thermal efficiency of that cycle. So we know the efficiency is defined by the desired output over the required input, right? In this case, because in chapter 9, we are talking about gas power cycles, and gas power cycles are used to produce work. So what we want for this kind of cycles is the net work output. Okay, so this is the desired output, and required input is just the heat addition, right? And the net work output is actually the Q in minus Q out from the energy balance, then over Q in. So that is 1 minus Q out over Q in. So exactly the same as what we have learned in chapter 6. Okay, so here says the ratio of the area enclosed by the cyclic curve. So the area enclosed by a cyclic curve, this is actually the net work out in this case, right? To the area under the heat addition process. Okay, so the area under the heat addition process curve, this is actually Q in. Okay, so the ratio of these two areas, that is the efficiency, right? The ratio of these two areas, one is the net work output, the other one is Q in, and their ratio is efficiency. Okay. All right. So Carnot cycle. Okay, so we know Carnot cycle is it's totally reversible. That means the Carnot cycle is internally reversible. It's also externally reversible. And we know there are 4 processes. So these 4 processes are isothermal, 2 isothermal processes, and 2 isentropic processes. 2 expansion processes. This is expansion, heat rejection. Well, heat rejection process, this is compression. Heat rejection is compression. So to expansion, heat addition is also an expansion, right? And then expansion, isentropic expansion or adiabatic expansion. Then heat rejection is compression. Then we have another compression. So 2 expansions, 2 compressions, 2 isothermal, and 2 adiabatic or 2 isentropic. So on a TS diagram, the Carnot cycle is a rectangle. It's a rectangle like this. Okay. So in chapter 9, we will talk about 4 cycles. Carnot cycles is the first one, but we have learned Carnot cycles. Then we will talk about Otto cycles. Then we will talk about diesel cycles. Then we will talk about Brayton cycles. Okay, so we will learn 3 new cycles. And for these 4 cycles, including Carnot cycles, you need to know how to make a PV diagram, how to make a TS diagram. So include every single detail as shown in this diagram. So you need to know this is isentropic, this is isentropic, this is Q in, this is Q out. On a PV diagram, you need to know these two are isentropic, and these two, they are constant temperature. Okay, and this is Q out, this is Q in. And state 1, state 2, state 3, state 4. So the relative position of these 4 states, you also need to know that. Okay, so this is very important for you to analyze the characteristics of this unique cycle. Okay, so Carnot cycle, Otto cycle, Diesel cycle, and Brayton cycle. So you will need to know these like 8 diagrams, right? So every cycle has 2 diagrams. It's 1 PV diagram, has 1 TS diagram. Okay. All right. So Carnot cycle, well, we know Carnot cycle can be executed in a closed system or a steady flow system. And either gas or vapor can be utilized as a working fluid. So Carnot cycle is literally the best. It's universal and it's totally reversible. So it's the most wonderful one. Okay, but unfortunately, it cannot be achieved in reality. Okay, and we have shown this before. We can rewrite the efficiency of a Carnot cycle in terms of temperature instead of Q in or Q out, right? And we have shown this. We have proven this in, I think, somewhere in the example in chapter 7. Okay. All right, this. Well, yeah. So show the thermal efficiency of a Carnot cycle operating the temperature limits of TH and TL solely. It's solely a function of these 2 temperatures. Okay, so exactly the same example as what we have learned in chapter 7, right? So efficiency is 1 minus Q out over Q in, right? This is how we define an efficiency, right? So 1 minus Q out, here is Q out. So you need to know how to make a TS diagram. So you know this Q out is actually the area underneath this process curve, right? So this area is Q out. Okay, so this area is TL times S2, let's say S3 minus S4, right? This is S3 minus S4. I am calculating the area of this rectangle, and this length is TL, right? Okay, so this is just the area. Okay, and Q in is this area. It's this area. So Q in is TH times S2 minus S1. However, S3 is the same as S2 because this process is isentropic. And S1 equals S4 because 4 to 1 is also an isentropic process. So these two are the same. So that means they are the same. So we can kill this. So the remaining is 1 minus TL over TH. Okay. So the efficiency of a Carnot cycle is a function of the temperatures. Okay, that's it. All right. Next, air standard assumption. Okay, so in gas power cycles, the working fluid remains a gas throughout the entire cycle. So that's why this is a gas power cycles. Okay, so spark ignition engines, diesel engines, and conventional gas turbines are devices that operate on gas cycles. So we want to make some assumptions on the gas we will be dealing with. Okay, look at this. So energy is provided by burning a fuel within the system boundary. That is the internal combustion engine, right? So they are internal combustion. Yeah, of course, they are internal combustion engines. But we don't deal with the combustion process because combustion is a super complicated process. Okay, so instead, we just use Q in to replace the combustion process. Okay, look at this. Air is predominantly nitrogen that undergoes hardly any chemical reactions in the combustion chamber. So the working fluid closely resembles air at all times. So we know air, 80% of air is nitrogen. Only 20% of air is oxygen. Okay, so nitrogen takes most part, 80% of air, and nitrogen is very difficult to have chemical reactions in the combustion process. So that's why we assume the air remains air. Okay, air is just air. We don't change the compositions of air even after combustion. Okay. All right. So the actual gas power cycles are complex. So we utilize the following approximations to simplify the analysis. So now air remains air. Okay. Then what is air standard assumption? First, the working fluid is air, of course, which continuously circulates in a closed loop and always behaves as an ideal gas. Okay, so air is an ideal gas. Air remains air, and air remains ideal gas. Okay, then all the processes that make up the cycle are internally reversible. Okay, that's why we call this ideal, right? This is ideal. The combustion process is replaced by a heat addition process from an external source. Okay, so we don't deal with the combustion because combustion is complicated. So we don't deal with the combustion, but we know the purpose of the combustion process is to supply some energy to the system. So that's why we just replace a simple heat addition process, okay, to replace the real combustion process. Okay. Then the exhaust process is replaced by a heat rejection process that restores the working fluid to its initial state. So we don't deal with the exhaust process as well. Okay, we just use a simple heat rejection process to replace the exhaust process. Okay, that would be easier. And this one, the last one, the most important. Okay, air has constant specific heat whose value are determined at room temperature. And if this condition applies, then we call this cold air standard assumption. So there's a code. Okay, so air standard assumptions, there's no code. Okay, so with or without code, there's a very big difference. Okay, and this difference is this. Air has a constant specific heat whose values are determined at room temperature. And we define the room temperature, which is at 25 degrees or 77 degree F. Okay. So when you see using air standard assumptions, then all these 1, 2, 3, 4, all these 4 assumptions are applicable or are applied to air. These are air standard assumptions. But if the problem tells you that using cold air standard assumptions, then you will need to apply this condition. You can assume the specific heats of air are constants. And these constants can be determined at room temperature. And room temperature is 25 degrees C or 77 degrees F. Okay. So again, cold air standard assumptions are a little bit different from air standard assumptions. And the only one difference is you can assume constant specific heat or not. In cold air standard assumption, you can do that. You can assume specific heats are constant at room temperature, which is 25 degrees. Okay, so this is a very important difference and very useful actually, because like in chapter 7, we know that for ideal gas, undergoing an isentropic process, then with constant specific heat, you have these 3 equations, very useful equations to use, right? So when the problem tells you that using cold air standard assumptions, then for the isentropic process, you can use these 3 equations. Okay. However, if the problem tells you that using air standard assumptions without cold, using air standard assumptions, then that means you will need to use this relation for the isentropic process. Okay, and that implies that you will need to use the tables. You will need to use the ideal gas tables to look for what you need. Okay, so this is a very, very important, very big difference between air standard assumptions and cold air standard assumptions. Okay. So let's talk about reciprocating engines. Okay, so first, reciprocating engines consists of a few piston cylinder devices. Okay, so this is just a very, very typical piston cylinder device. So you can see the piston can move up and down. Okay, so we have a few stuff to know. First one is called top dead center, TDC. So that means the position of the piston when the piston forms the smallest volume in the cylinder. So that means the piston moves to this position. Okay, so this is a TDC. So TDC is top dead center. So on the other hand, when the piston moves to this position, then this position is called BDC, bottom dead center. So when the piston is at the bottom dead center, the cylinder's volume is the largest. Okay, so it's the largest volume in the cylinder. Okay, then the distance between TDC and BDC is called stroke. Okay, so this is stroke. This is stroke. Okay, so it's a distance between the TDC and BDC. Okay. Then we have a few volume and one ratio. Okay, so first one is Clearance volume. So Clearance volume is the minimum volume formed in the cylinder when the piston is at TDC. Okay, so this is TDC. This line is TDC. So this volume is called Clearance volume. Okay, then displacement volume. Displacement volume is the volume displaced by the piston as it moves between TDC and BDC. So that is release volume. So this volume is displacement volume. So when piston moves to BDC, then like what here says, when the piston is at BDC, then the volume formed is the largest volume in the cylinder. So this so-called largest volume in the cylinder, including clearance volume and displacement volume. Okay. All right. Then we have a ratio called compression ratio. So compression ratio is a volume ratio. So it's defined by the maximum volume over the minimum volume. Okay. So or we could say this is VBDC over VTDC. Okay. All right. So this is just a few names you need to know when we talk about TDC or BDC or compression ratio. You need to know what that means, especially the compression ratio. Okay, we will be using this a lot. Okay, so compression ratio is a volume ratio. So it's a ratio of maximum volume to the minimum volume formed in the cylinder. Okay. All right. Then there's another name you need to know, which is mean effective pressure or MEP. So what is MEP? So look at this PV diagram. Okay. So this is the process curve. Okay. So we know the area enclosed by the process curve represents the network. It's a network. So we define a so-called MEP so that this area is also network. So these two networks, these two areas, they are the same. Okay. So you can see the network is MEP times the piston area times stroke. Okay, so piston area, I mean, this is piston's cross-sectional area times stroke. Stroke is the distance between TDC and BDC. Okay, so which is MEP times displacement volume, right? So displacement volume is this volume. So MEP times this volume it's the network. It's a network. Okay. So when you know what TDC is, when you know what BDC is, then if you want to compare two equal size engine, then you can just compare. I mean, you want to compare the performance of two equal size engines. All you need to compare is MEP. Okay. Because equal size means they have the same displacement volume. Then as long as the MEP is larger, that means the network output is larger. Okay. Right here. Okay, so yeah, MEP is a fake pressure that produces the same amount of network as that produced during the actual cycle. So MEP is a parameter that can be used to compare the performances of reciprocating engines of equal size. So equal size here means they have the same displacement volume. Okay. So the engine with a larger MEP delivers more network per cycle and thus performs better. Well, of course, okay, because when MEP is larger, that means the network is larger. If the displacement volume is a constant, that is equal size. That is what equal size engine means, right? Okay. Then we can classify the reciprocating engines by how the combustion process in the cylinder is initiated. One is spark ignition engine. We call SI engine, spark ignition. So that means the combustion is initiated by a spark plug. Okay. So another way to initiate the combustion is by compression. Okay, so we have another engine called compression ignition engine, or CI engine. Okay, so we will talk about SI engine and CI engine in detail. Okay, so spark, see this. So the combustion of the air-fuel mixture is initiated by a spark plug. So a spark plug is like to spark. So spark is just like very similar to lightning. Okay, so when you fire a spark plug, that means you initiate lightning. Okay, so lightning is like a very high density energy injected to somewhere, right? Okay, so most of gasoline engines are spark ignition engines. So if you have a motorcycle, most of the motorcycles, their engines are gasoline engines, and is the combustion of your motorcycle engine is initiated by a spark plug. Okay. In compression ignition engine, okay, so we know when you want to fire to burn the air fuel mixture, one way to go, well, using the spark plug. The other way to go that is if you compress the air, if you compress the system, you know the substance in the system, the pressure increases and the temperature increases. So just imagine if you have just for example, air fuel mixture in your cylinder, then you compress this air fuel mixture, what would happen? Well, the pressure increases, the temperature increases, right? So if you compress this system a lot, then the temperature would be higher than the auto ignition temperature of this air fuel mixture, right? So when the temperature is higher than this particular point, then this air fuel mixture will be burned. Okay, that means the combustion just happens because of the compression, just because of the compression. Okay, so most of the diesel engines are compression ignition engines. We will talk about diesel engines or diesel cycles later. Okay. All right. So now we are moving to SI engines. So the ideal cycle for SI engines is Otto cycle. Okay, Otto cycle. So don't forget this. And don't forget, ideal cycle in chapter 9 refers or implies it's an internally reversible cycle. Okay, so Otto cycle is the ideal cycle for SI engines. Okay, look at this. Most SI engines are four-stroke internal combustion engines. Okay, so the piston executes 4 complete strokes within the cylinder, while the crankshaft completes 2 revolutions for each thermodynamic cycle. Okay, so these 4 strokes are compression stroke, then expansion stroke, then exhaust stroke, and intake stroke. So let's look at this one by one. Okay. All right, this. Okay. So these are this is the diagram for those 4 strokes. Okay. So first one, well, I would like to go from this one. Okay. Even though this is the last stroke in this diagram, but because this is a cycle, so the cycle means it's just continue continue these 4 strokes. Okay, so I would like to start with this. Okay, so air-fuel mixture coming into the system, because when you pull this piston, you actually create a low pressure inside your system, right? Then this valve opens, then air-fuel mixture is drawn into your system. Okay. Then when you close both valves, this is closed, this is also closed. Then compression stroke means you compress, the piston compresses the system. Okay, so the pressure becomes higher, temperature becomes higher as well. Okay, then power stroke or expansion stroke. So expansion stroke or power stroke here means then you fire the spark plug to ignite the air-fuel mixture. Then air-fuel mixture is burning. Burning means you deliver or this kind of energy is released so that the piston is pushed away, right? So that means the piston or the system is doing work on the surroundings because the piston is pushing away. Okay. Then exhaust stroke. So we need to clean up the waste air-fuel mixture. So now this air-fuel mixture is burned, so it's useless right now. So we need to repel this gas, this exhaust gas, okay, so that we can draw a new air-fuel mixture. Then we continue these 4 strokes to deliver the power. Okay, so we can look a video that shows how these 4 strokes really work. Okay, but this one I think it's expired on the YouTube. So I replace the link here. I replace a link. Okay, so this link is different from what you have on hand, I guess. Okay, but I already have uploaded this new PowerPoint, these slides to the Moodle. So if you want, you can re-download. Okay, so let me click this. So this video shows you how a 4-stroke engine works. Okay.
A basic lesson in the fundamentals of a 4-stroke EFI gas engine may be helpful to your understanding of Mercury products. Here are the basic components of every 4-stroke gas engine. A piston, a connecting rod, a
crankshaft.
As the piston travels up and down in the cylinder, this lateral motion is turned into a rotating motion at the crankshaft. The longer the stroke of the piston, the larger the displacement of gas and air occurs in the cylinder. To propel that piston, we need to ignite a tiny bit of gas and a whole lot of air. This creates expansion inside the cylinder. The fuel delivery system consists of an air intake manifold, valves, intake and exhaust, a fuel injector, and a spark plug. A 4-stroke engine is called a 4-stroke because 4 up and down motions are needed to complete the cycle. In the first stroke, the piston travels downward as the intake valve opens and a mixture of air from the atmosphere and a metered amount of gas from the electronic fuel injector enter the cylinder. This is called the intake stroke. On the second stroke, the piston travels upward, compressing the air and fuel to make a highly combustible mixture. This is called the compression stroke. At this point, the spark plug fires, sending the piston downward from the expansion of the air and gas mixture. This is the combustion stroke.
So combustion stroke is power stroke.
The 4th stroke is the exhaust stroke. As the piston travels upward, the exhaust valve opens to release the burned air-fuel mixture. When the piston reaches the top of this stroke, the intake valve opens and the cycle begins all over again.
Okay.
All
right. So this is a very typical four-stroke engine. Okay. All right. So in the video, it takes the intake stroke as the first one, but it really doesn't matter. Okay. So we take compression stroke as the first stroke. It doesn't matter because it's a cycle. Okay. All right. So look at the PV diagram here. Okay. So this is the real process curve. This pink solid curve is a real process curves. So as you can see, this curve looks like a little bit complicated, but however, as we mentioned, if you want to analyze this kind of thermodynamic cycle, usually you will need some assumptions. Okay, so these assumptions are usually used to strip the irreversibilities. For example, at the TDC, well, let's look at this. First, we know the area enclosed by these process curves represents the network, right? In this case, is the network output. Okay, so as you can see, you have one network. You have another network. However, these two networks, if you compare these two networks, you can imagine this one is fairly small or relatively small when compared with this big one. Okay, so by some appropriate assumptions, usually we can ignore this part. And with straightening this part as a constant volume process, we can also approximate this part as a straight line, straight vertical line. Okay, things like this. Later we will talk about this in detail. Okay. All right. Another engine is two-stroke. So actually, at least we need two-stroke to finish this thermodynamic cycle. So most of the car engines are four-stroke engines, but some engines are two strokes. For example, like a very small engine, usually very small engine. Let me see. Let me. I don't know if you have seen this. Okay, so this kind of engine is usually two-stroke engine. It's small and it's compact, it's light, the geometry is simple, it's not too heavy, so you can carry on your back or something like that. Okay. All right. So all four strokes in a four-stroke engine can be executed in just two-stroke. So one is power stroke, the other one is compression stroke. Okay. So usually two-stroke engines are less efficient than their four-stroke counterparts. This is because the incomplete expulsion of the exhaust gases and partial expulsion of the fresh air fuel mixture with the exhaust gases. And like I just mentioned, usually two-stroke engines are relatively simple and cheap. Okay, and this is a good part. Have very high power to ratio power to weight ratio and power to volume ratio. So it's easy to carry on, and you can carry a two-stroke engine around. Okay, so it's suitable for small size and low weight applications. Okay, we can look at this video to see how a two-stroke engine works. Okay.
健达缤纷乐，哇，酥酥脆脆，绵绵滑滑，丝滑的牛奶
I
巧
cannot
克力，
skip.
酥脆微苦，含香浓榛果内馅，健达缤纷乐。
A two-stroke or two-cycle engine is a type of internal combustion engine which completes a power cycle in only one crankshaft revolution and with two strokes or up and down movements.
All right, look at this. Just look at this. So you can see this is the oh, sorry. Sorry.
A two-stroke or two-cycle engine. A two-stroke.
Oh, all right. So look at this. Do you see the small, tiny green arrow? Okay. So this is the intake. So this is the intake. So the green part, the green shading means air-fuel mixture. Okay.
Or two-cycle engine is a type of internal combustion engine which completes a power cycle in only one crankshaft revolution and with two strokes or up and down movements of the piston in comparison to a four-stroke engine which uses four strokes. There are usually three ports: an inlet port, exhaust port, and a transfer port. The transfer port connects the lower chamber beneath the piston to the upper chamber above the piston. The first stroke of the two-stroke petrol engine begins with the piston about halfway down the cylinder heading toward the top of the cylinder, going upwards. Because the piston is halfway down the cylinder, all of the ports are covered.
All right, look at this. So for a two-stroke engine, a piston is acting like a valve. Okay, so you can see when piston moves up, it covers the exhaust. This is the exhaust port. I cannot draw on. Let me see. All right. I think that would be easier. Yeah. So this is the inlet. This is the inlet, and this is the exhaust port. Okay. Then when piston moves up, then the piston can cover the exhaust port. So when combustion happens, then piston can move down, then let the exhaust port open. Okay. And at the same time, I mean, when moving down, then the piston covers the inlet port. Okay. Then push this green part passing through this passage into this combustion chamber. So originally, this combustion chamber has a burnt air-fuel mixture. Then this burnt air-fuel mixture will be expelled to the exhaust port, okay, because the new air-fuel mixture is coming in. So there's like we are using the new air-fuel mixture to repel the burnt air-fuel mixture. Okay, so that's why in the slide it says that the efficiency is usually low, because when you are doing this, you cannot guarantee that some of the new air-fuel mixture, fresh air-fuel mixture, would be expelled as well. Okay, so you kind of waste some new or fresh air-fuel mixture. Okay, things like this. Okay.
Because of the upwards motion of the piston, the bottom chamber below the piston falls below atmospheric pressure.
Okay.
As the piston moves closer to the top of the cylinder, it uncovers the inlet
So
port, which then,
when piston moves up, then this inlet port is open. So when piston is moving up, that means you are creating some low pressure underneath this piston. So draws or sucks some air-fuel mixture, new or fresh air-fuel mixture into this engine. Okay, so this is a two-stroke engine. All right. Okay, so now we are trying to make some assumptions, or we are trying to analyze the Otto cycle. Okay, so Otto cycle is the ideal cycle for SI engine. Okay, so we need to apply the cold air standard assumption. Well, not really need to be cold, but at least the air standard assumption. Okay, so in the air standard assumption, remember, we don't deal with the combustion process. We don't deal with the exhaust process. Instead, we use a Q-in. We use a Q-in to replace the heat addition process, which is the combustion process. We use a Q-out to replace the exhaust process. Okay. All right. So first one is compression process. So this compression process is adiabatic and reversible. So don't forget, ideal cycle is internally reversible. So so all these four processes are internally reversible. So for this compression process, because we make the cylinder adiabatic, so reversible adiabatic, that makes this process isentropic. So this is an isentropic compression. It's an isentropic compression. Okay. Then there's a heat addition. Okay. So this heat addition is maintained at constant volume. Okay. The position is holding in position. The piston is holding its position. Okay. So that's why this is called constant volume heat addition. Okay. Then because we have a Q-in coming, so the piston moves down, then that produces power. So this is an expansion process. Okay. So during this expansion process, we purposely assume that this piston in the device, this system is adiabatic. So adiabatic, reversible, that makes this expansion isentropic. So this is an isentropic expansion. Okay, and finally, we need to repel the burned air-fuel mixture, but we don't deal with that, right? We don't deal with the real exhaust repelling. Instead, we use a Q-out to represent the exhaust process. Okay, so this is a constant volume heat rejection. Okay, so if you make a PV diagram, so from state 1 to state 2 is an isentropic compression. It's an isentropic compression. So this is isentropic. 2 to 3 is a heat addition process, and it's maintained at constant volume. So this is a constant volume heat addition. Then 3 to 4 is an expansion, and this expansion is adiabatic. So this expansion is isentropic. Okay. Finally, 4 back to 1. This is an exhaust process, but we use a Q out. We use a heat rejection process to replace the real exhaust process. Okay, so this is a PV diagram. This is a PV diagram of an Otto cycle. Okay. On the other hand, for TS diagram, from 1 to 2, 1 to 2 is an isentropic compression. So this is a vertical straight line perpendicular to s-axis, because s-axis here is x-axis. Okay. So this is isentropic. Then 2 to 3 is heat addition process. Okay. So just to remind you that we know that heat addition increases the entropy of a system, right? If you have a system like this, there's a heat addition. So this heat addition increases the entropy. So the entropy change should be larger than 0. Okay. So 2 to 3, so 3 should be at the right-hand side of 2, right? That is entropy increase, right? Then 3 to 4 is isentropic expansion. So this is a vertical straight line as well. Okay. Then 4 back to 1 is heat rejection process. So if this system is there's a heat rejection, that means the system is losing heat, then the entropy change is smaller than 0. So entropy decreases. So entropy decreases, so we need to move in the direction of decreasing entropy. That is 4 back to 1. Okay. So again, you need to know how to make a TS diagram and a PV diagram for every cycle we are talking about. Okay, including Otto cycle. This is what we are talking about. And later we will talk about diesel cycle, then the Brayton cycle. Okay, so you need to know how to make a TS diagram, how to make a PV diagram. Okay. All right. Then once we know how to make these two types of diagrams, we are ready to do some analysis. Okay. So first one, the Otto cycle is executed in a closed system. The Otto cycle is executed in a pistons in the device. So it's a closed system. Okay. So the energy balance for any of the processes can be expressed as this equation. So this is basically just the energy balance. So we know energy balance is E in minus E out equals delta E system, right? Since this is a pistons in the device, which is a closed system, so the energy can be transferred by heat and work, right? So if you expand this equation, you would have Q in, work in, minus Q out plus work out, right? Equals internal energy change, right? Under a standard assumption, right? We neglect the kinetic energy change. We neglect the potential energy change. Okay, so the energy change for a system is just the internal energy change. Okay, then if we divide by the mass, then all these uppercase letters will be lowercase letters. That would be this equation. Okay. All right. Then if there's no work involved during two heat transfer processes, which is heat addition and heat rejection, right? This heat addition process, is under constant volume. This heat rejection process is also under constant volume. So there will be no work involved, okay? So for heat addition process, we can rewrite our energy balance equation using this, right? Because if there's no work involved, then Q in minus Q out is the internal energy change. So this is Q in, just Q in equals the internal energy change. And we know that the internal energy can be written in terms of specific heat and temperature. So that's why we can write in terms of specific heat and temperature, right? Delta U is CV delta T. Okay, so similarly for Q out, this is the energy balance equation between process 4 to process 1. Okay, or state 4 to state 1, because there's no work involved during these two heat transfer processes. Okay, so again, we can rewrite internal energy change using specific heat times the temperature change. Okay. Then what we are concerned is the efficiency. So based on the definition of the efficiency, so efficiency is the desired output over the required input. Okay, so in this case, all these engines are used to produce work. So we want to have the net work output. Okay, so we want to have net work output. Then the required input is just the Q in, right? This is the only one that input to the system. And the net work out in this case is Q in minus Q out based on the energy balance. Okay, so that's why the efficiency can be rewritten in terms of Q. Okay, then we know that we just learned that this Q in Q in is CV T3 minus T2. So Q in is CV T3 minus T2, and Q out is CV T4 minus T1. Okay, all right. So now look at this. With the air standard assumptions, with the cold air standard assumptions. So what does this mean? So with a word cold in front of air standard assumptions, that means we can assume the specific heats are constant at room temperature. So theoretically, not theoretically, but what we have learned before is like, all right, so U3 minus U2, it's supposed to be CV average times T3 minus T2, right? Because we know the specific heat varies with temperature. So, but if the temperature variation is not too much, we can use the average specific heat instead of performing a tedious integration, right? So similarly, U4 minus U1, it's supposed to be CV average T4 minus T1, right? So this CV average is average at T3 and T2, and this average is average at T4, T1. Okay. However, with cold air standard assumption, the specific heat can be evaluated at room temperature. which is 25 degrees. That means these two specific heats are the same. So we can kill the specific heat because of this, because of cold air standard assumption. Okay. All right. So we can rewrite the efficiency in terms of temperature, in terms of the temperatures at every state. Okay. Then we do a little bit rearrangement. Okay. So we take T1 out, we take T2 out here. Okay. So they are the same. We just rearrange. Okay. Then, all right. For process 1 to 2 and 3 to 4. So 1 to 2 is an isentropic compression. 3 to 4 is an isentropic expansion. Look at this. 1 to 2 is isentropic compression. 3 to 4 is isentropic expansion. Okay, it's ideal gas. Now we have constant specific heat, right? Under cold air standard assumption. Then these two processes are isentropic. So don't forget, ideal gas, constant specific heat, isentropic. We have three very useful equations to use, right? This, okay. Isentropic, ideal gas, constant specific heat. So we have these three equations to use. Okay, so now here we are using TV. We're using this. TV to K minus 1. So T1, TV to K minus 1 is a constant for process 1 to 2 and 3 to 4. Okay, so T1 V1 to K minus 1 equals T2 V2 to K minus 1. Okay, then we can rewrite using this format. Okay, then 2 to 3 and 3 to 4. 2 to 3 is a constant volume heat addition, right? And 4 to 1 is constant volume heat rejection. So constant volume means V2 equals V3. Then this is V4 equals V1. Okay, so V2 is replaced by V3. V1 is replaced by V4. Okay, then we just keep K minus 1 here. So, but 3 to 4 is an isentropic expansion. So it follows that T3 V3 to K minus 1 equals T4 V4 to K minus 1. So this is true. Okay. So this tells us what? This tells us that the ratio, this temperature ratio T1 to T2 is the same as T4 to T3. Okay. So this is what? This tells us that, okay, T1 over T2 is T4 over T3. Okay, then that means T3 over T2 equals T4 over T1, right? I just switch these two temperatures. Okay, so T4 over T1 it's the same as T3 over T2. Okay, That means what? That means these two guys are the same. So we can cancel them. Okay. So the efficiency becomes 1 minus T1 over T2. Okay. So 1 minus T1 over T2. T1 over T2 is V2 over V1 to K minus 1, right? So that means this becomes 1 minus V2 over V1 to K minus 1. Okay. If I make this upside down, so that is V, this is V1 over V2. I should write like this. V1 over V2 to K minus 1. Okay. And don't forget V1 over V2, sorry, I should go back to here, the compression ratio. Where's the compression ratio? Yeah, here. The compression ratio is V maximum over V minimum. And in this case, in this Otto cycle, let me see. V1 is the maximum volume. V2 is the minimum volume, right? If you look at the PV diagram. So V1 and V4, they are maximum. V2 and V3, they are minimum. Okay. So V1 over V2, this is actually the compression ratio. Okay. But don't forget, compression ratio is a volume ratio. But here, this is a lowercase v. So this is a specific volume. However, Otto cycle is executed in a piston-cylinder device, which is a closed system. So the mass doesn't change, right? So the volume ratio is the same as the specific volume ratio. Okay. So that's why finally we can rewrite this is 1 over R to K minus 1, and this is 1. Okay. The efficiency of an Otto cycle is a function of compression ratio and specific heat ratio. So K is the specific heat ratio, which is Cp over Cv. Okay. However, don't forget, we can go this far. We can write the efficiency of an Otto cycle in terms of compression ratio and specific volume ratio, is because we assume cold air standard assumptions. We have cold air standard assumptions, right? Because under these assumptions, we know that K can be evaluated at 25 degrees C. Okay, or otherwise, if you need to take the variation of the specific heat into account, then you will need a table, right? Because K is not a constant if you use just air standard assumption instead of cold air standard assumptions. Okay. All right. So this is a complete analysis of a cycle. Okay. So you need to know what this cycle is and the TS diagram, the PV diagram. Then you need to know what is the heat addition, what is the heat rejection, then you need to analyze the thermal efficiency of that cycle. Okay, so this is for Otto cycle. We will do exactly the same thing for the diesel cycle and Brayton cycle. Okay, and we will see that later. Okay. All right. So look at this. So now we know efficiency of an Otto cycle is function of compression ratio and specific heat ratio. Okay. So if you make a plot, look at this. Okay. So the x-axis here is the compression ratio and y is the efficiency. So as you can see, because you can see that efficiency is proportional, is inverse proportional to the compression ratio and specific heat ratio. Okay. So you can see that when the compression ratio is higher, then the efficiency will be higher, right? Clearly, okay. And on the other hand, if you look at the specific heat ratio, if we fix the compression ratio, right? If we fix the compression ratio, when the specific heat ratio is higher, then you would have a higher efficiency, right? So to increase the efficiency of an Otto cycle, you have two options. One, increase the compression ratio. Two, increase the specific heat ratio. Okay. However, there are some limits. Okay. There are some limits on increasing these two ratios. Okay. Look at this. For a given compression ratio, the specific heat ratio affects the thermal efficiency of an Otto cycle, right? Apparently, like this. For a given compression ratio, specific heat ratio affects the thermal efficiency. And we know when specific heat ratio is higher, then the efficiency will be higher. Okay. Now look at this. Okay. So an ideal Otto cycle using single atom gas as a working fluid has the highest thermal efficiency. So we know for most of single atom gas, the specific heat ratio is likely to be a constant at 1.667, right? So this is the maximum, this is the best we can go using single atom gas. However, where can you find a single atom gas as the fuel? That is the question, right? So the specific heat ratio decreases as the molecules of the working fluid get higher, get larger. So most of the fuel is made up of a lot of molecules, right? How can you find a single atom gas as a fuel? It's very unlikely, okay? Then next, the working fluid in actual engines contains larger molecules such as carbon dioxide. This is CO2. Okay, so like the second statement says, the specific heat ratio decreases when the molecules of the working fluid get higher. So if the gas contains carbon dioxide, then the specific heat ratio would be smaller than 1.667. Okay, so the specific heat ratio decreases with this is another point. The specific heat ratio decreases with temperature. So when temperature is higher, then the specific heat ratio decreases. And again, how did we get this equation? With cold air standard assumption, which we assume the specific heats are constants at 25 degrees. But in reality, the combustion when the combustion happens, the temperature inside the engine must be higher than the room temperature, of course. Okay, so this is actually the major reason that the actual cycles have lower thermal efficiency than the ideal cycle, because the temperature is much higher than what we assumed. We used cold air standard assumption to derive the efficiency of an ideal Otto cycle. Okay. All right. So the thermal efficiencies of actual spark ignition engines range from about 25% to 30%. Maybe it's higher now. Okay, but not too much. Okay. All right. Okay, so increasing the specific heat ratio is one way to increase the efficiency of an Otto cycle. Another way is to increase the completion ratio, right? Either increase the completion ratio or increase the specific heat ratio. Okay, so now you know the difficulties about increasing the specific heat ratio. Okay, now let's look at the problems induced if you want to use a very high completion ratio. Okay, auto ignition. Okay, so auto here means automatically. Okay, ignition is the way that we ignite the air-fuel mixture. Okay, so as I mentioned earlier, when the compression process is happening, then the temperature of the system increases, right? This is air-fuel mixture. Air, this is air. Air and fuel, air-fuel mixture. So when temperature increases, when you compress your system very, very hard, that means the temperature would eventually be higher than the auto ignition temperature of this air fuel mixture. Okay, that means you don't need to fire the spark plug to ignite the combustion process. That is bad. That is bad. Okay, so look at this. When high compression ratios are used, the temperature of the air-fuel mixture rises above the auto ignition temperature of the fuel. That means the fuel ignites without the help of a spark plug. Okay, so causing an early and rapid burn of the fuel at some points ahead of the flame front, followed by almost instantaneous inflammation of the end gas. Okay, then what happens if the auto ignition happens? It produces an audible noise called engine knock. Okay, it's engine knock. So engine knock is not allowable because engine knock hurts the performance and can cause physical damage of the engine. Okay, so that's why we cannot use a very, very high compression ratio, because we don't want to have the auto ignition. We don't want to have the engine knock. Okay, so that's why most of the typical engine, the compression ratio ranges from just like this, 7 to 10. Maybe now could go up to 11 or 12. Okay, but that's all. That's all. Maybe 12 is the maximum. Okay. All right. So to improve the thermal efficiency with lower chances of the auto ignition, we could do this. First one, high, of course, high compression ratios up to about 12. Then we can use the gasoline with some lead, So raising the octane rating, okay, octane rating is a measure of engine knock resistance of a fuel. So in Taiwan, usually we have 3 arc ratings at a gas station, 92, 95, and I think 98. Okay, so this is octane rating. Okay, but of course, if you want to have a very high octane rating gas, you need to pay more. Okay, you need to pay more. Okay, so another thing, use unleaded gasoline. But using unleaded gasoline, you will need to use low compression ratios. So this is a kind of a trade-off. Okay, compression ratio and the gas with very high octane ratings. Okay, it's a trade-off. Okay. Then let's look at the example here. So all the examples, all the problems in chapter 9 have a unique characteristic. That is basically you are looking for the temperature and pressure at every state. Okay. So once you have temperature and pressure for every state, you can have everything else, including the thermal efficiency, the MEP, Q in, Q out, or network output, things like this. Okay, so basically, all you need to do is find out what the temperature, what the pressure is for every state. Okay, so let's try this. We can see, just assume if you know temperature, if you know the temperature and pressure for every state, then look at the question. Okay, it's looking for the maximum temperature and pressure. Of course, if you know the temperature and pressure at every state, you can know at which state the temperature and pressure are the maximum, of course, right? Then the work output. Okay, for this is Otto cycle. So the net work output is Q in minus Q out. This is the network output, right? This is the network output. And Q in is between state 2 and state 3. So you know this is CV T3 minus T2. And for Q out is between 4 to 1, right? So this is T4 minus T1. Okay, so if you know the temperature, for every state, you can know the network output. Okay. Efficiency, well, efficiency is 1 minus Q in over Q out. Then you know the temperature, you know the efficiency. MEP. So MEP is defined by net work out. This is MEP times V1 minus V2. Okay. All right. So then if you know the temperature, you know the pressure, how do you know the specific volume? Don't forget, this is gas. This is gas power cycle. So don't forget PV equals RT. You know the temperature, you know the pressure. This is a gas constant. So you know temperature, you know pressure, you know the specific volume. Okay, so that's why I just said basically in chapter 9, all the problems are essentially to ask you to find out what the temperature and pressure is for every state. Okay, so let's try. All right. So this is an ideal Otto cycle. And here says the compression ratio is 8. Okay, compression ratio is 8. At the beginning of the compression process, pressure 100 kilopascal, temperature 17 degrees. Okay, so T1 is 17 degrees. P1 is 100 kilopascal. Okay, and Q in is 800 kilojoule per kilogram. So we know Q in is 800. Okay, now let's look at the pressure and temperature for state 2, state 3, and state 4. Okay, of course, you need to know process 1 to 2 is isentropic. It's isentropic compression. 2 to 3 is constant volume heat addition. 3 to 4 is isentropic expansion. 4 to 1 is constant volume heat rejection. Of course, you need to know that. You need to know that. Okay. So there's another thing you need to be aware of, which is here, accounting for the variation of specific heats of air. That means we cannot assume the specific heat is a constant at room temperature. Okay, so when you look, when you see this, accounting for the variation of specific heats, that means you will need to use tables. Okay, and for ideal gas undergoing isentropic process, then you have these two useful equations to use. This is exact. Exact in this case is accounting for the variation of the specific heats. Okay, that means you will need to use tables. Okay, so for isentropic process and ideal gas, we know the pressure ratio is the same as the relative pressure ratio. And the specific volume ratio is the same as the relative specific volume ratio. And pressure ratio, sorry, relative pressure and relative specific volume, they are a function of temperature only. So as long as you know the temperature, you should be able to get the relative pressure or relative specific volume, or vice versa. If you know the relative pressure or relative specific volume, you can use the table to derive to find out the temperature. Okay. So let's go back here. Okay. So in this case, we need to use the tables. Okay. We don't have these three equations because these three equations has to be under constant specific heat, this assumption. Okay. All right. So first one, we are looking for P2 and T2. So let me see. Okay, so the compression ratio is given. So compression ratio is given. That means V1 over V2 is 8. Okay. Don't forget, this is an ideal Otto cycle. So it's executed in a piston cylinder device, which is a closed system. That means the mass is a constant. So the volume ratio is the same as the specific volume ratio. Okay. So compression ratio is the volume ratio. It's supposed to be volume 1 over volume 2. But it will be the same as the specific volume ratio, V1 over V2, which is 8. And we know process 1 to 2 is an isentropic compression. So specific volume ratio is the same as relative specific volume ratio. So this is V1R over V2R. Okay. All right. Then T1 is given. So we can know V1R, right? Because T1 is given. So by looking at the table, we can find out what V1R is. Okay. So V1R is known. So we can get V2R. Just like what I said, we know, once we know the relative specific volume, we can use the table to find out the temperature, because relative specific volume is a function of temperature only. Okay, so now we know T2. Okay, Then don't forget about the ideal gas equation, PV equals RT. Okay, so in this case, P1 V1 over T1 equals R, right? This should be the same as P2 V2 over T2. Okay, so P1 T1 they are given. V1 over V2 is given, which is the compression ratio. Now you have T2, so you can get P2. Okay, so this is T2, P2. What about 3? Now we are looking for T3, P3. Okay. So then, all right. We know Q in is U3 minus U2. Q in is U3 minus U2, right? This is a constant volume heat addition. Okay, look at this. Q in is U3 minus U2. And don't forget, internal energy enthalpy of an ideal gas depends on temperature only as well, right? So we know T2, so we can know U2, right? And Q in is given, so we can find out what U3 is. Once we know internal energy, we can use the table to get T3 because internal energy depends on temperature only. In this case, this is gas, this is ideal gas. Okay. Then again, P2 V2 over T2 should be the same as P3 V3 over T3. Then because V2 and V3, they are the same. P2, T2, you have this before. Now you already have T3, so you can get P3. Okay, you can get P3. Okay, then let's look at this. T4 and P4. Again, we are using this again. V4 over V3 is 8, right? Because V4 is the same as V1. And V3 is the same as V2. Okay, so V4 over V3 is the same as the compression ratio, which is given. Okay, then this is V4R, this is a V3R, because 3 to 4 is an isentropic expansion. Okay, then you know V3. You know V3R because T3 is none. Okay, so you can get V4R. Once you have V4R, then you can use the table to get what T4 is. Okay, so once you have T4, P3, V3, T3 equals P4, V4, and T4. P3, T3. Then V3 to V4, V3 to V4 is 1 over 8. So you know this. Then you know T4, so you can know P4. Okay, so that's it. So you have T2, P2, T3, P3, T4, and P4. You got all the temperatures and pressures. Okay, so now you can easily determine which one is the maximum. Of course, at state 3, T3 and P3 will be the maximum. Okay, and the network output, like I just mentioned, the network output is Q in. Net out is Q in minus Q out. Okay, So Q in is U3 minus, well, this is given, right? Q in is given. Q in is 800. And Q out is U4 minus U1. You know T4, you know T1, so you can find the internal energy, okay, using a table. Okay, so this is the network out. And efficiency, 1 minus Q in over Q out. And again, this is 1 minus, Q out over Q in. This should be Q out over Q in. So this is U4 minus U1, and this is 800. Okay, and MEP, this is MEP. MEP is MEP times the displacement volume. That is the network out, right? So this is V1 minus V2. Okay, and V1 and V2, you can find out what V1 is, right? Because P1 V1 equals RT1. Okay, so we know R, we know T1, we know P1, so you can find V1, and V2 is V1 over 8. Okay, so you can get MEP. Okay, so yeah, that's it. So in chapter 9, you will need to practice this to find out what the temperature and pressure is for every state. Okay, once you have literally you have temperature, you have pressure, you can get anything else. Okay, you can get everything. Okay, so this is the ideal Otto cycle. Okay, next we are moving to another cycle called diesel cycle. Okay, so diesel, we know diesel, and diesel is actually a name. Okay, so Otto is a name as well. It's a name of a famous person. Okay, so of course diesel is. So diesel cycle is the ideal cycle for compression ignition engines. Okay, so the diesel cycle is it's the ideal cycle for CI reciprocating engines. Okay, the only one difference between CI engine and SI engine is the way that the combustion takes place. Okay, so for SI spark ignition engine, we need to fire a spark plug to burn the air-fuel mixture. But in compression ignition engine, we don't need to fire a spark. We don't need a spark plug, okay, to burn, to create, to ignite the air-fuel mixture. Okay, instead we use the compression itself. Okay, so we compress the air. Okay, well, let's look at the video. That would be clear, I think.
最划算的几10块币，输入优惠码首单5折。
口气 NG， 快工作也 NG， 立刻改用牙周式挥别牙龈问题。
All right, this is diesel engine. Okay. So the structure is basically the same or very similar as an SI engine. Instead, okay, so literally the only one difference, first one, not the first one, the only one is this. In a SI engine, this position is a fire, it's a spark plug. Okay, but in CI engine, this place is the fuel injector. Okay, so this is the difference. Okay, let's continue. Intake stroke. So TDC, BDC. All right. There's another difference. It's coming. So when the piston moves down, then it creates some low pressure system. The pressure inside the piston cylinder device is low. And see this. This is another big difference between SI and CI engine. So in an SI engine, what is being sucked into the piston is air-fuel mixture. But in this case, in this SI engine, what is sucked into the piston cylinder device? It's just air. It's just air. Okay. So look at this. Here says the piston pulls the air molecule into the cylinder. It's just air. This is air. This is all air, not air-fuel mixture. Fuel is not inside the piston at this moment. Okay, let's continue. So air is being sucked into the piston, into the system. Okay, then the valve is closed. Then the piston is compressing the cylinder. So this compression process increases the temperature and pressure of the air. So air is being compressed. Look at this. Here says compression raises the pressure and temperature of air to match the auto or self-ignition temperature of diesel. Okay, so what is being compressed is just air. So after the piston reaches very close to the TDC, then this fuel injector injects fuel into the air to mix with this air. Okay. So now ignition happens, combustion happens. Then pushing down the piston to produce power. Okay. So this is the power stroke. Then after that, the piston moves up again to expel the exhaust gases. Okay, that's it. Okay, so the schematic or the stroke diagram is exactly the same. Literally, it's the same as the stroke diagram shown for the Otto cycle. Okay. So now we can compare the differences between an SI and CI engine. Okay, so look at this. SI engine, the air-fuel mixture is compressed to a temperature that is below the auto-ignition temperature of the fuel. And the combustion process is initiated by firing a spark plug. Okay. But for CI engine, the air is compressed, just the air. And this is air-fuel mixture. Okay. So for CI engine, the air is compressed to a temperature that is above the auto-ignition temperature of the fuel. And the combustion starts on contact as the fuel is injected into this hot air. Okay. All right. So SI engine, a mixture of air-fuel mixture is compressed during the combustion stroke. So the compression ratio, compression ratios are limited by the onset of the auto-ignition or engine knock, right? So this is one reason that we cannot use a very high compression ratio in a SI engine. However, because CI engine relies on the compression, the high temperature as a result of the compression. So usually we can use very high compression ratio in a CI engine, okay, because only air is compressed during the compression stroke. Okay, so there will be no possibility for the auto ignition, right? We can compress air as much as we want. Theoretically, but of course there are other limits. Okay, but well, even though you compress the air to, for example, if you use like 100 compression ratio, what you are compressing is just air. Air is not gonna burn. Air is not gonna explode. Okay, so it's fine. So we can use very high compression ratio. Okay, but usually a CI engine can be designed to operate at much higher compression ratios. This higher, it means higher than the SI engines. Okay, so typically the compression ratio for a CI engine is between 12 and 24. Okay. So many of the stringent requirements placed on the gasoline can be removed, but fuels that are less refined can be used in diesel engines. So now diesel engines, well, the pollutants emitted from a diesel engine is much worse than the pollutants emitted by an SI engine or an gasoline engine. So that's why usually in the home use or the small sedans, hatchbacks, like home use cars, most of them are gasoline engines, okay, because of the environmental protection, okay. Only large vehicles, trucks, buses, things like that, or some special cars, they will need a very strong power. Then they are usually diesel. They are usually diesel engines, okay. But diesel engines do produce a lot of pollutants that are more toxic, okay, because the fuel is less refined, okay. All right. So the fuel injection process in diesel engines starts when the piston approaches TDC and continues during the first part of the power stroke. So the combustion takes place over a longer interval, okay, when compared with the SI engine, of course, okay. So the combustion is approximated as a constant pressure heat addition process. And this is the only one difference when compared with the Otto cycle. Okay, so Otto cycle, the PV diagram for an Otto cycle, the heat addition process is constant volume, right? This is a constant volume. Okay, but in a diesel cycle, this heat addition process is constant pressure. Okay, this is the only one difference, the only one process where the Otto and the diesel cycles differ. Okay, so don't forget this. Again, you will need to remember, you will need to know what is the PV diagram or what is the TS diagram for every cycle. So you will need to remember at least six diagrams. PV diagram, TS diagram for Otto cycle, that is the one. Diesel cycle, then later we will talk about Brayton cycle. So you will need to remember these three diagrams. Okay. So if you can remember the diagrams, then you should be able to know, you should be aware that the heat addition process in a diesel cycle is constant pressure instead of the constant volume, just like the SI engine, just like the Otto cycle. Okay. All right. So again, we need to analyze the diesel cycle. So we need to find out what is Q in, what is Q out, then what is the thermal efficiency, and how can we express thermal efficiency in terms of some kind of ratios. Okay, so let's try to do this. Okay, so now look at this. The amount of heat transferred to the working fluid at constant pressure and rejected at constant volume. Okay, so Q in is constant pressure and Q out is constant volume. Okay, so Q in is H2 minus H3 because this is a constant pressure process. This is Cp delta T. So Cp delta T represents the enthalpy change instead of internal energy change. Okay, so this is the only one difference when compared with the Otto cycle. Okay, then Q out is the same. It's Cv delta T is internal energy change. Okay. Then the efficiency. All right, so this is a little bit complicated. Well, of course, the definition is the same. Desired output over the required input. Okay, and the work output is Q in minus Q out. This is the same because this is the definition. Okay, however, things are different here. So Q out, now we know Q out is, we should say Q out, look at this. Q out is U4 minus U1 over CV times delta T. Again, here we are using cold air standard assumptions. Okay, so Q out, we can write Q out in terms of specific heat and temperature difference, right? So Q out is CV delta T. Okay, then what about Q in? Q in is Cp delta T. So let me rewrite this. Okay, let's try. So let me write here. So efficiency is 1 minus Q out over Q in. So this is 1 minus Q out is Cv T4 minus T1, and Q in is Cp T3 minus T2. Okay, and because we are using constant, sorry, not constant, cold air standard assumption. So that means CV and CP, we can evaluate this at room temperature, which is a constant. Okay, so CP, don't forget specific heat ratio is CP over CV. So if we move CV down here, then that would be 1 minus T4 minus T1, then K times T3 minus T2, which is this. Okay. Then we purposely do something the same as what we did for an Otto cycle. So we move T1 out of this, then T2 here. Okay, so we just do rearrangement. Okay, basically we just do the rearrangement. Then so again, the process 1 to 2 is isentropic. 3 to 4 is isentropic as well. Okay, so under cold air standard assumption, so TV to K minus 1 is a constant. Okay, so T1 V1 to K minus 1 equals T2 V2 to K minus 1, and T3 V3 to K minus 1 is T4 V4 to K minus 1. Okay, then you can rewrite this, right? T1 over T2 is this is V2 over V1 to K minus 1. Okay, then replace the specific volume, okay, using corresponding values, then you will have this. Okay, so I would just skip the some processes. Okay, let's jump to this conclusion. Okay, so the thermal efficiency can be written in terms of completion ratio and specific heat ratio, as well as there's a new ratio RC here. Okay, so RC here is defined by V3 over V2, which is called cutoff ratio. Okay, cutoff ratio. So cutoff ratio, if you look at the diagram here, so if this is V1, so V1 equals V4, this is a V3, this is a V2. Okay, so the completion ratio R is V1 over V2. Then a new ratio called cutoff ratio, cutoff. This is defined by V3 over V2. Okay. Okay, it's V3 over V2. So the efficiency, thermal efficiency of a diesel cycle can be written in terms of completion ratio, cutoff ratio, and specific heat ratio. Okay. All right. So well, look at this. So cutoff ratio is the ratio of the cylinder volumes after and before the combustion process, because this combustion process takes place under constant pressure. Okay, under constant pressure. So far, R is completion ratio, which is a volume ratio. Cutoff ratio is also a volume ratio. Okay. All right. So under the cold air standard assumption, now the thermal efficiency can be written in terms of these three ratios. Okay. So if you take a close look, you can see this is actually the efficiency of an Otto cycle. And this part is always larger than 1. It's always larger than 1. Okay, so that tells us what? That tells us that the efficiency of an Otto cycle is larger than the efficiency of the corresponding diesel cycle if the compression ratio is the same, if the specific heat ratio is the same. Okay. Well, specific heat ratio is the same because we are using cold air standard assumptions for both cycles, right? We use, so an Otto, sorry, eta Otto is 1 minus R to K minus 1. This is 1. So this is based on cold air standard assumption, right? And this is also based on the cold air standard assumption. So the specific heat ratio for these two efficiencies is the same. Okay. So under the same compression ratio, Otto cycle's efficiency is larger, is higher than the diesel cycle's efficiency. Okay. All right. So, but however, okay, we know that for Otto cycle, the typical compression ratio is it's ranging about from 7 to what? 7 to 10 or 11, right? But for diesel cycle, the compression ratio can be as minimum of 12. It's even higher than the maximum of the Otto cycle. So saying that under the same compression ratio, Otto cycle's efficiency is larger than diesel cycle's efficiency. Saying this is a little bit unfair to the diesel cycle, okay? Because the minimum compression ratio of a diesel cycle is essentially larger than the maximum compression ratio in an Otto cycle. Okay, so but no matter what, you can see that the diesel cycle, the efficiency of a diesel cycle is a function of compression ratio, cutoff ratio, and specific heat ratio. So if you make the compression ratio the same, then the efficiency of a diesel cycle is proportional to the cutoff ratio. Okay, if the cutoff ratio is 1, then this is reduces to an Otto cycle. Okay, then when cutoff ratio increases, then the efficiency of the diesel cycle decreases as well. Okay, so these two, I mean, RC and diesel cycles efficiency, they are inverse proportional. Okay, they are inverse proportional with each other. Okay. All right. So look at this. So diesel engines operate at much higher compression ratios and thus usually more efficient than gasoline engines. Okay, or usually more efficient than Otto cycles. Okay, so but you need to know that under the same compression ratio, the Otto cycle's efficiency is larger than diesel cycle's efficiency. However, because of the physical limits, the minimum compression ratio of a diesel engine is larger than the maximum compression ratio of a gasoline engine. Okay, that's an interesting point. Okay, so when you hear someone tells you that a diesel engine, a diesel car has a higher thermal efficiency than your gasoline engines, you can say something against him, okay, or against her, whatever, okay, because saying this usually more efficient than gasoline engine. That is because diesel engines operate it's much higher compression ratio. If diesel engine operates at the same compression ratio as gasoline engines does, then gasoline engines efficiency is higher than the diesel engine's efficiency. Okay. Now look at this. So diesel engines burn the fuel more completely since they usually operate at low revolution per minute, and the air-fuel mass ratio is much thinner than gasoline engines. Okay, so this is about fuel, about some chemical. Okay, so thermal efficiency of large diesel engines typically range from 35% to 40%. It's larger than the typical efficiency of a gasoline engine, but this is because diesel engine has usually they operate on high compression ratios, right? Okay. All right. So look at this. So far we approximate an Otto cycle using, heat addition process. For an Otto cycle, we use constant volume process, right? This is Otto cycle. And diesel cycle, the heat addition process is approximated by a constant pressure process. Okay, so look at this. So approximating the combustion process in internal combustion engines as a constant volume or a constant pressure heat addition is overly simplistic. Okay, so a better way, but slightly more complex approach is to model the combustion process as a combination of two heat transfer processes, one at constant volume. One is at constant volume, this is like this one. And the other one is at constant pressure. This is a constant pressure. So this is called dual cycle. It's called dual cycle. So like we combine constant pressure and constant volume process together. Okay, so this is dual cycle. Okay,